Hey guys, welcome to Safi Mixed. In this video, I want to derive the equation of motion um, for mass sliding on an inclined plane, and would derive the relation for velocity as a function of time and as a function of position along the inclined plane. So to this end, I consider this situation. This is the horizontal, and I take an inclined plane which is making angle theta with the horizontal, and I place a block of mass m on this plane. Okay, first I consider the simplest case that there is no friction between the block and the inclined plane. So if we look at this, there are two forces acting on the block. One is the weight of the block, which is equal to m times g, and the other is the normal force or reaction force of the plane, which we denote this with n. So we can solve this problem by choosing our coordinates axis along at the intersection of the plane and mass, such that in the direction of the plane we have x-axis positive, and this side x prime, that is negative axis. To this direction we have y, and to this direction we have y prime. Then we learned in our previous video on the inclined plane, and if you don't know, I will add if you don't know, click on the link in the description to this video, that this angle is always equal to theta. So I can write, since there are only two forces, one is weight and the other is normal force, therefore the net force on the block is equal to Fg plus N. And this net force, according to Newton's second law, must be equal to mass time acceleration, which I can also write as m times r double dot, where r double dot is the position of the block from this origin along the plane. Now obviously there is no force acting in the upward direction, therefore the block, if it is sliding, must be sliding down. So what we do, we can split this equation into two components, one along x-axis and one along y-axis, and I can construct two scalar equations. And that I do by considering this thing, f g x I plus f g y j, where I is the unit vector along x-axis, j is the unit vector along y-axis. This I'm writing for fg plus n x I plus n y j, and on this side I would have m into x double dot I plus y double dot, not the vector over here, not the vector j. That would be the situation. And I can separate on this side the x and y components, and can write this as f gx plus nx into I plus f gy plus ny into j equals m x double dot I plus m y double dot j. Now I can compare the x and y components, or I can first project this equation to the x component by multiplying with I dot, and then projecting this to y's axis by multiplying scalarly with j. So whatever way you may do, I can write if gx plus nx is equal to m x double dot, and if gy plus ny is equal to m y double dot. So I have two scalar equations. Now we need to find fgx, nx, fgy, ny, and similarly x double dot and y dot. So for that, what I do, I resolve this force along x and y axis. That I can do by dropping a perpendicular on the y axis, right? So this component is parallel to x axis, therefore that gives me if gx, and this one is parallel to y axis, this gives me if gy. And for n, there is no component along x axis because this is parallel to the negative y axis, therefore we don't resolve that. So from this I can write that nx is equal to 0 and ny is equal to n. And from here, now this is a right angle triangle with hypotenuse equals mg, and this is the base because we have the angle at that side in here is 90 degrees. So if gy from this right angle triangle is in fact equal to mg cos theta, and this thing is equal to mg sine theta. So from the components I can write if gx is equal to mg sine theta, and if g sub y is equal to mg cos theta. So if I put these values, and one thing more, since there is no motion along y-axis because the block would remain on the plane, therefore y double dot is equal to 0. So putting these values in equation 1 and 2, I can write 1 and 2 in the modified form like this. For f gx, I write mg sine theta. For nx, I write 0, so that is there is nothing, and I write m x double dot. I call this equation 3. And from here, if gy is equal to mg cos theta, right? And then ny is equal to n, so but that n is along negative, so I have a minus sign over here. That is along the y prime axis, therefore I will put minus n, and y dot is 0, this is equal to 0. I call this equation 4. From here I can write mg cos theta is equal to n. So this equation says that this component is exactly equal to this component, and these two components are this equation does not contribute into the dynamics of the mass. So only this equation describes the motion of the particle, and for that I can write x double dot, that is the acceleration, is in fact equal to mg. I'm switching the sides of the equation and then taking m2 and then divide by m, so that allows me to write this as x double dot equals mg sine theta, or this gives me g sine theta. So we have the acceleration A equal x double dot equals g sine theta. Now g is constant, theta is fixed, so this term is constant, therefore we have a constant acceleration. And from this acceleration, we can derive the equation for velocity, time dependency of velocity, and position dependency of velocity. So first I want to solve this for velocity as a function of time. And for that, I can write this equation as dx dot over dt equals g sine theta. Or I can write dx dot equals g sine theta dt. Now, let at time t equals 0, the velocity is 0. The block is just starting motion. And at time t equals t, the velocity is vt. Then integrating this side and this side between the corresponding limits, I can write v naught equals 0 to vt dx dot equals g sine theta. Because g and sine theta are constant, I take t equal to 0 to t dt. So this gives me x dot from 0 to vt. I'm writing the t and substitute mean velocity at time t is equal to g sine theta, and this is t, the limit is from 0 to t. So if I put the limits, that gives me v at t equals g sine theta times t. So this equation tells us the velocity at any time t, where this is the acceleration. So that means we found velocity as a function of time. So we can find the velocity at any time using this one equation. And now I want to find a relation for velocity in terms of the position along the plane of the block. So that I can do by, again, I'm removing these things, and this is not needed anymore to me. I can multiply this equation with 2 times x dot. That is, I want to write this equation in the form 2 times x dot into x double dot equals 2 times x dot g sine theta. And let me do this thing. If I differentiate x double dot square, what do I get? I get 2 times x dot into x double dot. So that means this is in fact the derivative of this thing. So I write, for this I write d x dot square over dt equals 2g sine theta, and this I'm writing as dx over dt. Now I can drop this and this, the dt in the denominator, and can just write this as x dot squared equals 2g sine theta dx. Now let at x naught is the position at the origin, which is 0. At x naught equal to 0, the velocity at that point is 0. That is, I use these conditions, x naught equal to 0. This means that the velocity, which I write as v naught equals to 0. And at x equals x sub t, the velocity is v equals v sub t. Then I can integrate this equation between the limits d x dot square from 0 to, remember I'll write vt square because I'm differentiating x dot square, therefore the limit must be vt square from 0 to t square using this and this. And this would be equal to 2g sine theta integral from 0 to x sub t dx. Right? I'm integrating this thing. This gives me x dot square from 0 to v sub t square equals 2g sine theta, and this gives me x integral with limit x is equal to x sub t. And if I put the limits, I write v at t squared equals 2g sine theta x sub t, from which I can get v sub t equals square root 2g sine theta xt. So this equation gives me the velocity as a function of position along the plane, and the previous one which I read about was giving the velocity as a function of time. So this way you can link the velocity with position along the plane and with time sliding on the plane, with time as the block slides on the plane. And the end. Thanks for watching.